Okay, so we will get started. And I'm gonna go back and forth between the slideshow and actually working the notes on the overhead. So we're going to talk about chapter 4, which is probability. And the thing I want you to remember about chapter 4 is if you don't overthink it, it will be much easier. People tend to want to overanalyze probability because they've heard that it's hard, it's terrible. It doesn't have to be. If you'll just kind of let your logic flow, it can be very common sense. So don't overthink it. That's the best piece of advice I can give you. You are going to have to practice with this. This is not something that comes naturally to anybody. So it's going to be a little more challenging maybe than the first 3 chapters were. And you're going to have to take some really good notes. So the first thing we want to do is we want to get down some definitions. And if you've got your notes in front of you, most of this is just kind of filling in the blanks. And then when we get to the examples, I'll do those up here on the overhead. So the first thing we'll talk about is what is a sample space, what's an event, what's a simple event, and how is that different from what we call a compound event. The sample space is all of the outcomes for which the event can't be broken down any further. And one of the simplest events that you can think of is just simply tossing a coin. If you toss a quarter or a nickel or a dime or a penny or whatever, if you toss a coin, there's only 2 things that can happen as an outcome of that coin toss. It either lands heads up or it lands tails up. If you draw a card out of a shuffle deck of 52 cards, there's 52 different outcomes for that because there's 52 very different cards in that deck. So the simple event is the outcome that can't be broken down into simpler components. But if I have a compound event, the compound event then is, for example, maybe I'm going to flip a coin and then draw a card. Or draw a card and then flip a coin, which is pretty much the same thing. You're going to have the same kind of probabilities. You'll have a different probability or a different number of outcomes for one of the events from what you do for the other one. And there's rules for how we figure out what probabilities are where you've got 2 simple events that are combined into one compound event. So the event is just a collection of results or outcomes. For example, if I toss a coin 4 times, the outcomes might be 4 heads. Or it might be a head and 3 tails. Or it might be a tail and 3 heads. Or it might be 4 tails. Or I could have 2 of each. So there's a lot of different outcomes. And the whole sample space consists of all the different possible outcomes. Now the notation we're going to use, P represents probability. A, B, and C are usually what we use to represent some event because we get tired of writing out the probability that it is a blue marble. We'll just probably write P and then parentheses blue because we don't want to have to write out all those other things. So A, B, and C just denote the outcome of something, some event. P of A denotes the probability that that event occurs. So for example, if A is the event from my sample space that I toss my coin and it lands heads up, then A is the coin lands heads up, and P of A is 1 over 2 because the coin's only got 2 sides and one of them is a head. And we can change that 1 over 2, which is 1/2, to either 0.5 or to 50%. So the event H here, we would write P of H if we decided to, instead of using A to stand for heads, we could let H stand for heads. But you don't read that as multiplication. That's the big deal. The parentheses do not indicate you're multiplying anything. It's just saying the probability of whatever's in the parentheses. The first thing that we're going to talk about is called the fundamental counting principle. The fundamental counting principle helps us because it will help us figure out, if we have two events that we're looking at together, how many ways can those two events happen together? How many different outcomes might they have? And what the rule says is that if one event can occur in m ways, for example, the coin toss, m would be 2, and a second event can occur in n ways, let's say I'm going to roll a 6-sided die, so then n would be 6 because there's 6 faces on the die. Then the number of ways the two events can occur, if I toss the coin and roll the die, the number of different outcomes would be m times n. So if I tossed a coin and then rolled a die, the number of ways that those events could happen together would be 2 times 6, or 12. Because I could toss a head and then the number 1, or a head and then the number 2, or a head and the number 3, and a head and the number 4, and so forth. So all this is a way to count those without having to actually list them out. Sometimes it's helpful to make something called a tree diagram. A tree diagram is a picture of all the possible outcomes of a procedure, and we do it with line segments branching out from one starting point. They're helpful in determining the number of possible outcomes in a sample space, as long as the number of possibilities isn't too large. If it's too large, then a tree diagram gets to be too awkward and too cumbersome. Okay? So we'll do some examples here. And here's our first example. Let's see if I can make that a little bigger. So our first example says, how many rolls are possible when rolling 2 dice? Okay, how many is not a hard question to answer. You have 2 dice. Each one of those die has 6 possible outcomes. The numbers 1, 2, 3, 4, 5, 6. So how many is simply 6 on the first die and 6 on the second die. So that will be 36 different possible outcomes. And I know it seems like that's an awful lot when you've only got two little cubes with 6 possibilities each. But you have to remember that there's a lot of different ways those dice can land. And one of the best ways to think about how that could happen would be if one of those dice was red and the other one was green, because then you could definitely tell that there's a difference in the outcomes, even though they look similar if all you do is write the numbers. So if I suppose that my green die has 6 different possible outcomes, that would be 1, 2, 3, 4, 5, 6, but then so does my red die. So while it would be possible to have 1 and 1 and a double 1 or 2 1s, that's really not going to look any different regardless of which one hit the table first. But 1, 2 doesn't look anything at all like 2, 1. Because a green 2 and a red 1 is not the same as a red 2 and a green 1. Okay? That's where a tree diagram actually comes in to be very handy. So to picture the tree diagram, we have the green die. And that's everything that can happen. And I can't even fit this one all on one piece of paper and make it easy enough for y'all to read. Now, if I roll a 1 on the green die, on the red one I could get a 1, a 2, a 3, a 4, a 5, or a 6. But the same thing can happen with the 2. And it can happen with the 3. So while 1, 1 looks like 1, 1 no matter what, 1, 2, 1, 3, 1, 4, 1, 5, and 1, 6 is my first 6 outcomes. So that's a 1 followed by another 1, a 2, a 3, a 4, a 5, or a 6. And this would be 1 outcome each. But if my 2 comes first, that could be paired with a 1, a 2, a 3, a 4, a 5, or a 6. So my first die says 2, but my second one is different for every time. So these are all different outcomes. And what I want you to notice here is, first of all, that outcome is a green 1 and a red 2. This one is a green 2 and a red 1, and they don't look the same. They're not the same. And that's going to happen with every single one of these. 3, 1, 3, 2, 3, 3, 3, 4, 3, 5, 3, 6. The first number in every one of those pairs is 3. But the second one is again 1, 2, 3, 4, 5, 6. And notice here that 3, 1 doesn't look anything like 1, 3. And 2, 3 doesn't look like 3, 2. The order is different. And if you imagine that they're different colors, you can see why they're different. So notice what happens here every time is I've got 6 different possibilities for the first die, but then I've got 6 more possibilities for the second one. So this gives me 6, and plus 6 more is 12, plus 6 more is 18, plus 6 more is 24, plus 6 more is 30, plus 6 more is going to be 36. And rather than having to go through that, it's much, much easier to realize that it's simply 6 times 6, which is going to come out to be the 36 different possible rolls. And the only thing that the tree diagram lets me do is it lets me actually list out all the different rolls. And I may not need to list all of those out. I may need to just know simply that there's 36 of them. So that's why that little shortcut rule is very handy to have. So our second example says, baseball manager has 5 pitchers and 2 catchers. How many different possible pitcher-catcher combinations can that manager put out on the field? So he's got pitcher number 1, 2, 3, 4, 5. But for every one of those pictures, there's two different possible catchers. So that's a total of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And it's much easier just to say, well, if I don't really need to know what they look like, then it's 5 times 2 is 10. Unless I need to know the actual combinations, I just need to count them, then that's all I need. I need to know how many. Does anybody have any questions on that so far? Okay, our third example. Suppose you're packing to go on vacation, and you pack the following items. You pack 2 pairs of pants, a black pair and a tan pair. You pack 3 shirts, 1 red, 1 white, 1 yellow. And you pack 2 pairs of socks. Now, assuming that you can wash these clothes whenever you need to, how many different outfits could you come up with? How many days could you go without having to wear the same outfit twice? And the answer to that is calculated with the MN rule. 2 times 3 times 2, which is 12 outfits. With an outfit being 1 shirt, 1 pair of pants, and 1 pair of socks. Okay. Now, if we wanted to know what those outfits actually looked like, we'd have to build that tree diagram. And the first set of our tree would have 2 branches for the 2 pairs of pants, and then the second part would have 3 branches coming off each of those 2 for the 3 different shirts, and then each one of those would have to have 2 more branches coming off of it for the 2 different pairs of socks that you put on. So you could list them out, but that would take a while. We don't usually need to do that. So I'm not going to make a tree diagram of that, although we could. We don't really need to. Now here's one that might seem like it probably has more importance for the everyday person. Suppose you've got a security system for your house that has a 4-digit access code. How many access codes are possible if each digit can only be used once? Now the first question you've got to consider is how many digits are there? What is a digit?
0 to 9.
Yeah, it goes 0 to 9. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Single numbers. Okay? And there's a total of 10 digits. 1 through 9, and then the 0 makes the 10th one. So we can use each digit only once. So what we've got is we've got 4 choices. First number, second number, third number, fourth number. How many choices do we have for the first number? We have 10 different choices because there's 10 numbers. Now it says we can't reuse whatever we chose for the first one. So how many choices do we now have for the second one? Only 9. And since we can't reuse either one of those, how many choices for the next one? We only have 8. And then for the last one, we lose another one, so we only have 7. And you can use your calculator to confirm this, but it comes out to be 5,040 different access codes. And I sure wouldn't want to make a tree diagram that shows what all those access codes are, much less have to write them all down. But it's helpful to know that there's 5,040 of them, because if my security system calls the police after you punch in the wrong code 3 times, what's the likelihood somebody that doesn't know the code to get into my house is actually going to get that code right and get in my house before the police get called? Not too good, right? Because each individual time only has a 1 over 5,040 chance, which is a very low probability. And even all 3 of them together, you know, that's only 3 out of the 5,040 different codes before they're going to call the cops. So your access codes can really be a good protection for you. Now the next one is a similar situation, but it says how many codes are possible if each digit can be used more than once, but the last one can't be 0. That's the only restriction. The last one can't be 0. All the rest of them could be 0. All the rest of them can repeat, except the last one can't be 0. So what does that change about my number of possibilities? Okay, the last one would be 9 choices because I don't get to use all 10 digits. But what about the first 3? They're all 10. So 10 times 10 times 10 is 1,000. Times 9 is 9,000 different codes. Where this was only, and I say only kind of jokingly, 5,040. So by allowing repeats, even with the restriction of not being allowed to use 0 for the last one, I got almost double the number of codes. And that means it's even less likely that somebody can break in. Okay? But the thing to keep in mind is the more restrictions you put on the possibilities for the codes, the fewer codes you're going to be able to use. For example, same thing, you've got a 4-digit access code. How many can you have if the first digit can't be a 5 or a 7? That means you only have 8 choices. And the last digit has to be odd. How many odd numbers are there 0 through 9? 1, 3, 5, 7, and 9. So 5 odd numbers. And if the challenge had been even, if it had to be even, this is one thing I'll bring up to you now. 0 is not even. The even numbers are 2, 4, 6, 8. But 0 itself is not even. So if you're talking about digits, there's 0, and then 4 even numbers and 5 odd numbers. So since it says first digit can't be 5 or 7, okay, that leaves me with 8 numbers. Last digit has to be odd, that gives me 5 numbers. These can be anything. So it's going to be 8 times 10 times 10. And that's going to be 800 times 5, so that's only going to be 4,000 codes. But that's still enough codes that I don't think the thief is going to get in her house. Not with just 3 tries.
Unless he just breaks the door down.
Yeah. The alarm's going to go off then anyway.
Yeah. What's this one? Will he be able to get away?
That would be the question. With my 2 big dogs in the yard, I doubt it. Okay, let's talk about probability. we're gonna go back to the PowerPoint for a minute. It's wrong place. First thing we need to talk about probability before we go to the examples is something called the law of large numbers. The law of large numbers says that in the long run, as the sample size or the number of times you repeat some probability experiment increases, the relative frequencies of the outcomes are going to get closer and closer and closer to what's called the classical or the theoretical probability. Now what that is a fancy way of saying if you toss a coin 10 times, you think probably you're going to get 5 heads and 5 tails, right? But you wouldn't be too surprised if you got 6 heads and 4 tails, or 4 tails and 6 heads. You wouldn't be shocked if you got 7 heads and 3 tails, or 3 heads and 7 tails. But if you only got 1 head and 9 tails, or 9 heads and 1 tail, you might be a little surprised. You might wonder if that coin was fair, or if the person tossing it knew something you didn't know. So the question becomes, not are you going to toss the coin 10 times, because that's not a very large sample. But what if you toss the coin 1,000 times, or 10,000 times? Well, what's going to happen is the more tosses you get, the closer the percentage of heads to tails is going to be. They're going to both be pretty close to 50%. It might be 49% for one and 51% for the other, or something, a little off, but it's going to get really, really close. And actually, that thought was arrived at by a famous mathematician that liked to play cards. His name was Descartes, and he was imprisoned for cheating at cards, believe it or not. And he had time on his hands, and he was also a great probability theorist. So he actually, while he was stuck in jail, flipped the coin all day, every day, and kept track. And wound up, I think, flipping the coin the last time that I remember reading the history, because that's one of the things math majors do, is we have to take the history of mathematics, and that's one of those interesting things you find out. He actually flipped the coin 50,000 times. And his probability was amazingly close to 0.5 for the heads and 0.5 for the tails. So, he must have had a good coin. So what it means basically is, if you flip a coin 20 times, the actual number of heads you might get is 8, which is really only 40%. But if you flip the coin more and more and more and more times, like maybe instead of 20 times, 20,000 times, chances are you're going to get heads about half the time, or 50% of the time, which is what it should be. And I wish I could tell you that little probability applet worked, but it doesn't. I clicked on it and the link's broken. Because it actually shows flipping a coin, and it shows the probability leveling out to 0.5. This is the most important part of your notes. Draw a box around it, draw circles around it, put big stars on it, use your highlighter. These you need to know. And fortunately, these are relatively common sense. Probability is always a fraction or a decimal between 0 and 1. It's always a fraction or a decimal between 0 and 1. And because it's a decimal, we can convert it to a percent, which will be between 0 and 100. The probability of an impossible event is 0. If I tell you the probability is 0, that means it's not going to happen. No way, no how. Can't happen. It is impossible. The probability of an event that is absolutely certain, guaranteed to occur, is 1. That means it is absolutely going to happen. There's no way it can't happen. Both of those generally are rare. There are very few guarantees in life that either something does or doesn't happen. Everything else has a probability somewhere between 0 and 1. There are no probabilities that are greater than 1, because that would be more than 100%, and nothing can happen more than 100% of the time. Probabilities can never be negative, because negative probabilities, just think about it, they don't make any sense. If it's impossible for something to happen, the probability is 0, so what would a probability of negative 10% mean? It would be meaningless. The closer the probability is to 0, the less likely it is to happen. The closer the probability is to 1, the more likely it is to happen. If I can only teach you one lesson in probability, it's all right there. That's really all you need to get through in life, is to know that much about probability. But since we're going to talk about probability a little bit more, we're going to talk about some other terminology, especially since we are in a state and in an area and in a country where there's a thing called the lottery that's very popular. So I'd like for you at least to know why you're wasting your money when you buy the lottery ticket. First thing, and I can put all of this in terms of the lottery, complement consists of all the outcomes for which the event A does not occur. The notation the book uses it for is A with a line over it. I'm not really big on symbols. I'm more likely to write P, not A, because I know what not means. And I might confuse the line with being the average of A. So I would just as soon use words. I don't like symbols. Basically, that first thing here says is that the probability of an event plus the probability of its complement is 1. Now think about it. Either the event happens or it doesn't. Either A happens or it doesn't happen. I flip the coin and either the head comes up or it doesn't. Guaranteed something's going to happen one way or the other. That's why it's equal to 1. 50% of the time I expect heads, 50% of the time I expect tails. Assuming that the person tossing the coin is fair and that the coin itself is fair. That also means that if you know the probability something will happen, you also know the probability it won't happen, because you can just subtract that from 1. So to go back to our example problems here for a minute, suppose you roll 1 die. What are the outcomes for 1 die? Well, let's list the outcomes first. You're right. You're right. But the possible outcomes, if you roll the dice, you either get a 1, a 2, a 3, a 4, a 5, or a 6. Probability that it will not land on 3. 1, 2, 3, 4, 5 left. So all that rule is telling you is what common sense tells you. A recent survey shows that 64% of all third graders bring their lunch to school every day. What would the complement of that be? 64% do bring their lunch every day. So 1 minus 64%, and actually that's 100 minus 64 since it's percent. So the probability that they don't bring their lunch is 36%, because 64% do bring their lunch, okay? And either they bring it or they don't. That's the only conclusions you can come to. Don't overthink this. I've had people ask me, well, what if they didn't bring their lunch, but they bought lunch at the vending machine? Doesn't matter, they didn't bring their lunch. Okay? That's the only thing you can say for sure is 36% of them don't bring their lunch. You don't know what they do for lunch. They just didn't bring it. And we're also going to talk about something about probability and odds. And rather than go back to the PowerPoint for this one, because I know you've got the formula on your handout, I want you to understand the difference in what probability looks like and what odds look like. Because if you buy the lottery ticket or you gamble, you go to Vegas, odds and probability are related, but they don't sound at all alike. And it's easy to misinterpret odds if you think that they're corresponding to probability, because they really don't. They come from probabilities, but saying them is actually misleading. Find the probability in a classroom that has 12 boys and 10 girls. What's the probability that you randomly choose one of the kids' names out of a hat and that kid turns out to be a girl? How many girls are there? 10. And how many students are there? So 10 out of 22. We normally express probabilities either as a fraction or a percent. As a decimal, it's 0.45454545 forever. And if we change that to a percentage and round to one decimal, then the probability of choosing a girl is 45.5%. And you kind of have a sense of what that means. There's a pretty good chance you'll choose a girl. There's a better chance you'll choose a boy, but there's a pretty good chance you'll choose a girl. Okay? This one says find the odds of choosing a girl. The word that would need to go in there to make it really clear, find the odds in favor of choosing a girl. Because there's two kinds of odds. There's odds that favor an event, and then there's odds against the event. So if you want to find the odds that favor an event, it's basically the comparison of the probability of an event and the probability of its complement. And there's two formulas. If the odds favor the event, then the probability of the event goes on top. If you're trying to find the odds against the event, then the probability of the event doesn't happen goes on top. And the complements go on the bottom of the fraction. So let me show you in the example how that works. Find the odds, and that's why I said it was important to put in favor of, because it says the odds of choosing a girl, so you're looking for choosing a girl. So that means the probability of a girl will be the probability that goes on top. And the probability of not choosing a girl is going to go on the bottom. Of course, it should be fairly obvious that if it's not a girl, what is it? You're going to have to say that's the same thing as the probability of a boy. So that means the probability of a girl, and here we're going to go back to the fraction. is 10 over 22, and that's going to be divided by the probability of not choosing a girl, which is going to be 12 over 22. And we generally don't like 4-story fractions. So what we're going to do, not to have to deal with that, is we're going to rewrite this it's actually the same as a division. This is divided by. So rather than write that as a fraction that's really a division problem, we're going to change it into a multiplication problem. When you have a fraction divided by a fraction, you flip the second fraction over and you multiply. And when you multiply, look what happened. Now, we don't write the answer as a fraction because odds are not expressed as fractions. Odds are never expressed as fractions or decimals or percents. The expression of this would be 10 to 12. Basically, that means there's 10 chances of getting what you want and 12 chances of not getting what you want. Okay? If you want to find the odds of choosing a boy, the interesting thing that you'll notice is you don't really need those odds formulas at all. Because what happens if I'm finding the odds of choosing a boy, that's the same thing as the odds against choosing a girl. So the odds of choosing the boy are 12 out of 22 over the odds of choosing a girl, which is 10 over 22, which is 12 over 22 times 22 over 10. So that gives us the odds of 12 to 10. So the more common sense way to think about odds is how many ways can what you're trying to calculate the odds for happen compared to how many ways does it not happen. So you don't really need to do all that fraction business every time. The odds of choosing a girl are the number of girls compared to the number of boys. The odds against choosing a girl are the number of boys, which are not girls, compared to the number of girls. You're always just comparing two numbers. This is what's called better than even odds because you have more chances of getting the boy than you do of getting the girl. When you're talking about games of chance, the odds should be even. 1 to 1, 10 to 10, 5 to 5, 13 to 13, if it's a fair game. However, if you go count up all of the odds to any of the games of chance that anybody plays, they're never fair. We'll continue on with our examples for a few minutes. We're going to keep talking about this same group of marbles, so I want you to tell me before we go too much further, how many marbles are in that bag? Okay. Keep that in mind because that's going to stay the same through everything that we do. Find the probability of drawing a blue marble. Three blue marbles over 19 marbles. Not very good. Not a high probability. So we would say the probability of drawing the blue marble is equal to 3 over 19, which is 0.1578, which is enough for us to say that that's 15.8%. And that's always how you round probabilities. You initially go to 4 decimal places so that you can round it to 3. When you change it to a percentage, you'll still have 0.1%. The next part says, however, find the odds in favor of drawing a blue bead. How many blue beads? 3. This is where you got to be careful. How many of the beads are not blue? 16. So the odds in favor of drawing a blue bead are 3 and 16. Not 3/16, 3 in 16. That's the way it's actually expressed. Find the odds against drawing a pink bead. How many beads are there that aren't pink? 14. And there's 5 that are. So your odds are 14 to 5. Okay? That tells you you don't have a very good chance of drawing a pink bead. The odds favor against pink beads. And once again, be careful and watch your language. Is it odds or probability? Because this says find the probability, not the odds, probability of drawing a bead that's not white. That's everything but white. There's 7 white ones. So the not white ones are 12 out of a total of 19. Which is 0.6315. Or 63.2%. Think you got this so far? Let's do a couple more. Find the odds in favor of blue or white. That means we want to count the blue ones and count the white ones. 3 blue, 7 white. So there's 10 in favor to 9 that are not blue or white. And then we're back to probability. Find the probability of drawing a yellow bead. And there's 4 yellow. So that's 4 over 19. Which is 0.2105. And that'll be 21.1%. Any questions? We're gonna go back to the PowerPoint for a minute because we got some more words to talk about now. I already told you at the very beginning, we're just repeating this here, that a compound event is any event that combines two or more simple events. So it's two different events that we're considering the probability of both of them or neither of them or one or the other of them happening. Okay? The idea of disjoint or mutually exclusive is usually troublesome for people. So I want you to think through this with me and pay careful attention here. Take good notes. Disjoint means not joined, not overlapping, not the same, not joined in any way. Two distinct, separate things. These diagrams help, but they don't help much in real life. This is disjoint. There is no overlap. This is not disjoint. In this case, things are either red or they're yellow or neither one. In this case, things are maybe red, maybe yellow, maybe both red and yellow, or neither one. Okay? There's two rules here for those, and I don't even want you to look at the rules. I'm going to come back and talk to you after the examples and kind of show you how the examples can explain this to you. This is commonly confused with disjoint. Remember, disjoint means this can happen or this can happen, but they can't both happen at the same time. That's really the way to remember. Disjoint or mutually exclusive means if one happens, the other one can't. They can't happen at the same time. Okay? Independent events is not the same definition. Independent events means that one doesn't have any influence over whether or not the other one can occur. One doesn't influence the probability of the other. Now, if A happens, B can't happen. Did A influence B? If A happens, B can't happen. Was there influence? Yeah. And if B happens, A can't happen. There was influence. So disjoint events are not independent. They are very much dependent. They do influence each other's probabilities because one can keep the other one from happening. So with that said, now we'll go to the examples, and I'll try to show you with examples how one is different from the other. And I'm going to close that because that's going to drive me nuts popping up every time. So here we've got some events. And we don't need the calculator for this because we're not calculating any probabilities. We've got three events here. Event A is that we're going to randomly select a person that's a female student. We're thinking about eventually the probability of A, but right now, A happens if we select a person who is a female student. Okay? Event B is we select the person that works full-time. We're randomly picking students from some class, and event B happens if the person that we pick works full-time. Event C happens if we select a person that is unemployed. They don't have a job at all. They're unemployed. Are events A and B disjoint? Can you select a female student who works full-time? Then they're not disjoint. They can occur at the same time. Okay? Don't get those confused. Disjoint means that they can either be a female or they can work full-time, but not both. Okay? Disjoint means but not both. Either or, not both. So events A and B, female and full-time working, are not disjoint. And what's important is not just that the answer is no, it's why the answer is no. No, because female students can work full-time. You could select a female who is working full-time. Now we're going to compare events B and C. Are those two disjoint? Yes, they are. Because you can't be unemployed and work full-time. Okay? It's that whole idea of but not both. You can be one or the other, but you can't be both. So events A and C are not disjoint also. Because you can have a female student who is unemployed, just like you can have one that works full-time. Okay? So it's the idea that they're disjoint if they can't be both. If both can't happen on one single occurrence. Now I'm going to ask a different question that's not on here and it's not on your notes. Are events A and B independent? Is there any reason to believe that being a female means you're more or less likely to be employed full-time? Is there any reason to believe being employed full-time makes it more or less likely that it's a female student we selected? No. So those events are independent. What about B and C? Are they independent? If you're working full-time, does it make it more or less likely you're unemployed? If you're working full-time, can you be unemployed? No. So does it influence the likelihood that you're unemployed? Yes. It keeps you from being unemployed. And if you're unemployed, that keeps you from being employed full-time or working full-time. So those are dependent events. Disjoint and dependent go together. If you have two events that are disjoint, They are going to be dependent upon each other. Now, the fact that they're not disjoint doesn't mean that they're independent. Don't take it to mean that it works this way. But this one works. If they are disjoint, they will be dependent. So here's a couple more examples. Let's suppose event A is that we roll a 2 on a die. And event B is we roll a 5 on the die. Our events A and B, we're only going to roll it once. It says roll a die, one time. Our events A and B, mutually exclusive. Yes, because you can't have a 2 and a 5 come up on the same roll. And I should say here, you can get, it doesn't guarantee you will, but you can get a 2 or a 5, but not both on one roll. It's the idea they can't both happen simultaneously. Now that's going to make a difference in how we answer this question. And I want you to associate some words here. I want you to associate the word or with addition. Okay? And this should hopefully make sense when we think about it. Here's what could happen. We could roll a 1, a 2, a 3, a 4, a 5, or a 6. How many ways can we get a 2? How many ways can we get 5? So there's 2 ways we can have this happen, right? Two out of 6. And you can write that any of those 3 ways. Now there is a rule. I will tell you, there is a rule that says the way you do this problem is you find the probability that you roll a 2 and you add it to the probability that you roll a 5. And the probability you roll a 2 is 1/6. And the probability you roll a 5 is 1/6. And that's 2/6. And so forth. Did you need to know that rule to figure that out? No. You know, you can get a 2 or a 5, and that's 2 different rolls. And there's a total of 6 different possibilities. So the answer was obviously 2 out of 6. You shouldn't need some rule to tell you what you can figure out for yourself. Okay? Don't make this harder than it is. The one thing I'm going to discourage you from in chapter 4 is please, please, please don't memorize rules. Only use the rules as a last resort, because they're confusing sometimes. Sometimes they'll make you second guess yourself and make you put down an answer that's wrong when the answer you thought was right to begin with. Okay? So don't just, if you can figure it out without a rule, don't use a rule. Draw pictures. Pictures are worth 1,000 words. This one's a little bit harder. If you can figure this one out, you've got this whipped. YMCA has an enrollment of 4,563 people. That's the total number of members. From the total number of members, we have some that play on the basketball league. 852 play in the basketball league. We also know that of the 4,563 members, 3,041 of them are males. But now here's the hitch. If you're looking only at the members of the basketball league, that 852, 520 of those are males. And they're also a member of that 3,041. Okay? So when we think about that, the first question we have here, are the events selecting a male and selecting a male that's a member of the basketball league disjoint? Or could you select a male that is on the basketball league? Are there men on the basketball league? That's really all that's asking. Make sure you understand that's really what that question's asking. Are there men in the basketball league? And the answer is yes. They're not disjoint. And they can occur at the same time. You can pick a member out of the YMCA, and that member may be a man on the basketball league. So that's not separate groups. There are men that are on the basketball league, there are men that are not. But you can select a man that is both. He's male and he's on the basketball league. Disjoint means that he either can be on the basketball league or he's not a man. Okay, that would basically say that there was only women in the basketball league. Men couldn't join. The fact that these are not disjoint, they do overlap, means if we answer probability questions about this, we have to be careful. We have to be very careful. Because we have some men that are being counted as a part of both groups. And we can't count them twice. So if we select YMCA members at random, we're going to choose one. Find the probability the person we select is either a male or they're in the basketball league. Now the first thing that you would think about doing here is say, okay, how many men are there? Okay, there's a total of 3,041 men. You say, okay, that's good. How many basketball members are there? 852. So altogether, you think, well, that would be 3,893. Right? Why is it not that much? Yeah, you counted them as being men, you can't count them again if they're in the basketball league. So 520 of these men got counted here. They also got counted here. We double counted them. They were in both categories. So then we have to subtract out that 520. So in reality, there's only 3,373 men or basketball players. I cannot spell EA. So anybody that you counted as being in both, you have to actually subtract them out one time. They don't get to be men and basketball players. They don't get to count twice just because they do two things. Okay? So that means our probability of male or basketball is 3,373 out of the total 4,563. Which is still a pretty good probability. So there's 73.9% chance that you'll select somebody that's either a male or they're on the basketball team. Okay. One more. Remember, don't overthink these. Event A is that we randomly pick somebody that's 6 feet tall. Event B is that we randomly pick somebody that has blonde hair. Are they, one, mutually exclusive? Are being blonde and being male disjoint or mutually exclusive? Those mean the same thing. Why not? They are not disjoint. Why not? You can be a blonde male. Remember, disjoint means separate. You can be this one or this one, but you can't be both. Okay? So no, they're not disjoint. They can occur at the same time. Are they independent? Are you more likely to be blonde if you're 6 feet tall? Are you more likely to be 6 feet tall if you're blonde? So are they independent? Yes, they are independent. Hair color doesn't influence height, or vice versa. So they are independent. They are not disjoint. A person can be 6 feet tall and be blonde. Okay? Practice those with some examples because you're going to need to be able to distinguish both of those different terms. Now this is a different example. It's the same kind of a question. Suppose you're going to throw a fair die and flip a coin. What's the probability that you roll a 3 and your coin lands on heads? here's the key word. And this actually goes back to that fundamental counting principle, but it's easier this time. I am going to tell you to memorize some words. And means multiply. Or means add. And means multiply. Or means add. And means both. And means one or the other, which is why you have to add them together to get probabilities. And is the other one, and you have to multiply. There's not a rational way for me to tell you that that's how it works. Just, it does. And means multiply. It always means multiply. It means you're going to multiply the probabilities. What's the probability of rolling a 3? What's the probability you get ahead? And means multiply. Now, I can't explain to you why it's true. But you'll trust me when I tell you this is always how you do it. And it's going to go back to that tree diagram thing. I'm going to roll a die. What can happen? You agree with me? That's everything that can happen. 1, 2, 3, 4, 5, 6. Okay, now I'm going to flip a coin. So here are all the different outcomes that we could have. You roll a 1 and you get a head. You roll a 1, you get a tail. You roll a 2, you get a head. You roll a 2, you get a tail. You roll a 3, you get a head. You roll a 3, you get a tail. You roll a 4, you get a head. Well, you can roll a 4 and get a tail. You can roll a 5 and get a head. You can roll a 5 and get a tail. You can roll a 6 and get a head. You can roll a 6 and get a tail. How many is that? That's right. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 different outcomes. Which one is this? And that's the only one. So here's your choice. You're either going to have to make the tree diagram, list them all out, and count, or trust me. Associate the word and multiply. That way you don't have to draw it all out. Okay? So now we practice. Suppose you got a deck of 52 cards. If you are someone that is not familiar with cards, don't play cards, you don't know anything about cards, you can send me a text and let me know, and I'll explain to you some things you need to know about cards, because not everybody does. But basically the things you need to know is there's 4 suits: hearts, spades, clubs, and diamonds. And there's an ace through 10, ace, 2, 3, 4, 5, 6, 7, 8, 9, 10, and a jack, king, and a queen in each one of those. That's where there's 13 of each suit, 4 suits. We want to find the probability of drawing a king and an ace, but we're assuming that we're going to draw the first card and not put it back. We're going to draw the first card out of the deck, lay it on the table, then we're going to draw a second card. Because the answer to this, if we were only going to draw one card, would be 0. Because there are no kings and aces on the same card. This is a question about if we draw 2 cards out of the deck, what's the probability we draw a king and an ace? Okay, the probability of the king is 4 out of 52. How many cards are left in the deck if I lay the card I drew on the table? There's only 51 cards left. How many aces are left in the deck? There's that word. And. Four out of 52 times 4 out of 51. Now, I know y'all just love to do fractions, right? Everybody just loves fractions. I know that's the biggest knot there is. If you have the 83, put your fractions in parentheses. Always, always, always put fractions in parentheses. If you have the 84 and it has the numerator over denominator, if you've got one of the newer ones that actually makes a fraction out of it, you don't have to. But if you've got an 83 or you're using one that, like we've got on the computer, put your fractions in parentheses. And if it says, give me the answer as a fraction, not a decimal, if the problem says, give me the answer as a completely reduced fraction, and my math lab's going to say that, this is how you do it. You hit the math button, and the top one says change the answer into a fraction. So the answer is 4 out of 663. Now, if it says it's okay to put it as a decimal, then it's 0.0060. Which is less than 1%. It's 0.6%. Now, there was a lot of lessons there. Lesson about how to change fractions, so that you don't have to do fractions in your head and you don't have to memorize how you reduce fractions and all that stuff. There was the lesson about multiplying. There's one thing that's very important that you need to understand about why you multiplied and why you made some assumptions that you may not have realized you made. I assumed that the first card that I drew was a king, which meant that I assumed that there were still 4 aces in the deck. Okay? that word can be misleading, and normally if I write this, my question will be worded this way. Because a king and an ace could have occurred two different ways. I could have got an ace first and then drawn the king. The probabilities would have been the same. But in order to make it plain to you, you have to think about it that I'm going to draw a king and then an ace to realize how you have to make the changes. You have to assume that you drew the first card and got what you wanted. Otherwise, it doesn't matter what the second draw is. You're not going to get a king and an ace. So you have to assume that your first draw, you got what you first said you wanted. Okay? I think I'm going to do the same thing with y'all that I do with my morning class. You have this worksheet. You don't need a single rule to answer the questions on this worksheet. This worksheet lets you figure these out by looking at the picture. I'm going to go through the first one with you. And that's all I'm going to do. And I'm going to have you work on this for practice so I can let you go a few minutes early because you didn't get a break. And I want you to finish this up on your own and bring it back with you. And then we'll do contingency tables, which will be the last part of chapter 4, and we'll go ahead and work on chapter 5 next time too. Okay? But this is how you do this worksheet. Find the probability a randomly selected snowman is wearing a scarf. How many of those snowmen are wearing scarves? 8. How many snowmen are there total? So the answer is 8 over 18. Okay? Read the question. Count the snowmen. As long as you get this finished by the time I see you the next time, you're free to go.